Okay, guys. Someone said Diophantine equations are very difficult to solve. I will show you it's not. This is a very famous, in certain domains, this is a very famous equation. And I want to give you the connection to control systems through this example. My goal today is to cover first this Diophantine equation and connection to controls, and then start the convergence analysis of the PAA parameter estimate. Let's start with something that you all know how to do. Suppose I'm using the transfer operator notation, but you can use the same notation, change Q with Z to go back to the discrete time transfer function notation. But suppose I have a plant that looks like this. It has an integration inside. And then I want to design a controller. From your undergraduate controls, you know I can design, for example, using the technique of pole placement, which is basically saying that I'm going to try a numerator-denominator pair for the controller. And if I want my closed loop poles to be at certain locations, this is what I can do. I'm going to assure, so the closed loop transfer function from R to Y, you can see this is quite simple. And then this is negative feedback. So this is the transfer function. And the closed loop poles come from the characteristic equation. If I want my closed loop poles to be at 0.5, then what I need to design is, so design the characteristic equation to be such that it's going to give me a pole here. So here is the desired closed loop pole, how it's going to come from. Then I essentially need to solve for C and D, these two polynomials, to make this happen. Now, let's try. I'm going to say, so I'm not making something that's too complex. I just say the closed loop pole to be at 0.5. So let's suppose this is my desired goal. Then I can see this is a first order term. And on the left, I will be sufficient. It seems I will be sufficient by supplying two first order designs over here. So let's try C1. I don't know the coefficients yet. So I'm going to do this. And I don't know the coefficients for D yet. I'm going to design like this. Okay? So the design goal then will translate to 1 plus D1 Q negative 1, 1 minus Q inverse plus so that's going to be our design goal. Just substitute everything inside. This is one equation, but this is really more than one equation. I need to make sure that the coefficients for all the terms, Q negative 1, and then this is the constant term. Then I need to make sure the coefficients, so it's another Q to the power of negative 2 term. I need to make these coefficients to match on the left and on the right. So essentially, I need to achieve 1, so let's talk about the constant coefficient. It's going to be 1 times 1, then that's the only constant term from the first part. I have another constant term, C1, C0, and that's my goal for the constant term. So this is Q0. And then for Q inverse, the coefficients should be let's do some math. If you multiply this out, you're going to get a negative Q term, 1 times negative Q inverse, plus D1 Q inverse times 1. So it's going to be negative 1 plus D1. These two terms, that will be the coefficient, define the coefficients for Q inverse. And then there's another C1 on the left. It has to match negative 0.5. And then lastly, Q to the power of negative 2 term. There's none from here. There's 1 from here. It's D1 times negative 1, so it's negative D1. That's the left side. The right side, I have none, so it should be 0. So therefore, you can see that this very specific solution from here. I need C0 to be 0. I need D1 to be 0. And I need C1 to be 0.5. Some simple computation. So that would be an undergraduate control design. And it's quite feasible. So the final controller that we will achieve is numerator is going to be 0.5 Q inverse. Denominator is just 1 because D1 is 0. All right? So a simple delay operation will achieve a close to pole design placement at here. And it's powerful, right? This is a marginally stable system, and I can stabilize it at this location. Actually, if you try with 0.8, 0.9, 0.6, it wouldn't matter. You will be able to solve this equation set. You can try that. So that seems quite nice. And if you see how the operation goes from one polynomial equation to 3 linear equations about these coefficients, then you have essentially touched upon this class of equations. All right? And the benefit, the most important thing from the first topic today is that giving some Planck polynomial numerator and polynomial denominators is guaranteed. We can do this pole placement arbitrarily at any locations as long as they satisfy certain conditions. So that's quite powerful. And the conclusion, the result, the fact is this. If, let's now be more general, let's say if my plant satisfies BZ and AZ are co-prime, and in other words, they don't have common factors. They don't have common roots. Then let's say the order of this is m. The order of the denominator is n. And m is less than or equal to n, just to be realistic. Then it's guaranteed. Can do arbitrary pole placement. For choose the controller to be with a controller, feedback controller. CZ over DZ. And the orders are CZ needs to be n-1 order and then -1 order. This is the maximum of the orders. That's how exactly I chose. The maximum order here is 1. So I chose C and D to have a maximum order of 1, and it worked out. So that is the fact. I said something that's not exactly correct. I said I selected the maximum order to be 1 here to match the order here, which is the example that I did. But throughout this analysis, actually you can see I just need to choose. I don't have to select D to go all the way to polynomial. I need D1 is essentially 0. So there is some space actually optimization that we can do. We don't need to do a full order to have the order of the controller to match exactly the order of the plant. So one small correction. So let's use the Diophantine equation approach to understand this. Why can we have guaranteed solution for this pole placement? And the key is in here. This control design is nothing but a set of linear algebra. All right? So let's take a look at the general case. Let's say generalizing let's say I use my same notations. This time I'm going to write it in more complete form. Let's say the controller, the plant is beta over alpha, and then they are defined as numerator is beta 1 to beta n, nth order with inherent delay, one-step delay, so matching our realistic physical system. And then alpha is 1, alpha 1, alpha 2, alpha n. Okay? So not all of them has to be non-zero. For example, if beta n is 0, then the order of the numerator is n minus 1. So it doesn't have to be exactly nth order. This is a general sufficiently general representation. Then pole placement, the Diophantine equation is defined as follows. Associated to this, we do a polynomial equation. We have a, let's do alpha suppose the controller would be sigma and gamma. All right, so the block diagram construction is as follows. The Diophantine equation is the characteristic equation here with gamma z, alpha z, sigma z, alpha z, gamma z, and beta z. It is to conceptually to design the closed loop polynomial, characteristic polynomial to be eta. And then the notations are, the orders are sigma is going to be from 1, sigma 1, sigma n minus 1, and then gamma is gamma 0, gamma 1, all right? So again, the numerator and denominator, the first coefficient for the denominator is normalized to 1, similar to the coefficient here. And the target closed loop polynomial is 1 all the way to gamma eta 2n minus 1. All right, so that's the complete set of equation. Let's take a look first. Let's check the orders. The order on the left side, the highest order is n minus 1 plus n. So it's going to be 2n plus 1, 2n minus 1, n minus 1 plus n here. So it's 2n minus 1, the highest order. And on the right is also 2n minus 1. So the order match, first of all. Then the solution, so will look like this. Let's write out the equivalent set of linear equations corresponding to this polynomial equation. So essentially, we do the same operation. We multiply these polynomials out. Now, this time, I want you guys to understand it from a linear algebra or matrix viewpoint. The multiplication for this one, let's see, is going to be then alpha here. I'm going to do it not directly write out the long equation, but I'm going to do it in a way similar to how we wrote down the coefficients in the example. All right. We know the highest order is going to be 2n minus 1, and then the lowest order is going to be a constant coefficient. The parameters actually can be entirely obtained from a matrix viewpoint like this. So usually we know the coefficients for the plant. So alphas are the knowns. The unknown that we're trying to solve is this sigmas. So I'm going to write it in this way. All right? So I'm going to somehow in the end come up with a matrix multiplying with a vector. And the vector contains all the unknown coefficients that we want to solve. And the known coefficients alpha will go inside this matrix. So that's my goal. And let's check. So the coefficients for the constant, this is quite easy, right? It's going to be, there's only one way to generate a constant coefficient, which is these two multiplied together. If you multiply this with any of these, you can't get a constant coefficient term. So it's going to be 1, 0, etc., 0. And then the second term, the way to get z negative 1, there are two ways. First is this 1 multiplying with this term. And then second is the sigma 1 multiplying with here. So I'm going to have alpha 1 multiplying with 1, which is here, this pair. And then do this one, sigma 1 multiplying with 1. That's the only two possible ways. So it's going to be 0 afterwards. Do a few more, I think you will find some pattern. For this one, z negative 2, there are 3 ways now. First is 1 multiplying with the alpha 2 z negative 2. So it's going to be alpha 2 multiplying, so this is the first coefficient here, 1. And then there's alpha 2 z negative 2 here, plus sigma 1 multiplying with this alpha 1, right? So it's alpha 1 here. And then finally, sigma 2 here multiplying with what? It's going to give me a z negative 2 term. 1, right? So it's 1. And then nothing else, right? Anything you try to pick sigma 3, that's going to be a third order term now. So it's going to be 0. You can do this, and then in the end, you're going to know that it has a pattern. So you can see this sort of diagonal, this 1 element keeps marching down, and these alpha terms keeps marching down in a diagonal way. So the end result is this. Make it slightly longer. Okay? So, two things. First of all, this matrix, I intentionally made it a little bit taller. The dimensions has to match. So it's going to need to have n columns, right? There are n elements here, so it's going to have a dimension of, first of all, is n columns. How many rows should I have depends on here. It needs to have 2n minus 1 plus 1, so it has to have 2n rows. So therefore, it is a tall matrix multiplying with a vector. And then these are just the zeros in the entries that I don't specify. All right, so we did a couple of examples at the beginning. Let's check in the end the final term, the last coefficient. Let's check this one too, just to see that the structure works. So the only way to generate the z negative 2n minus 1 term is from this multiplying with this. So the coefficients has to be alpha n times sigma n minus 1, right? So that actually works. So all 0 until you hit alpha n times sigma n minus 1. So it has this interesting structure. On the left, right, it's a bunch of zeros. On the bottom left is also a bunch of zeros. Then it has this diamond shape in the middle. So this is really just the linear algebra if you do this multiplication. This is for the first term. You can do the same for the second term. And the result is going to be something similar. The unknowns are, in this case, gamma. Beta is known. Gamma is the one that I try to design. So it's gamma 0, gamma 1, gamma n minus 1. And then it's going to have the same shape. Beta is here. The first coefficient for the constant term is 0, so it's 0. And then beta 1, beta n, 0, beta 1, beta n, marching down. Beta n, and then everything else is 0. So that's the structure. Now, to make these coefficients match, finally, we got to combine these two matrix vector multiplications together. So watch out how the way that we can make these combine together. What we want now, sigma alpha now we know it's going to be able to be represented in a gigantic matrix vector multiplication. And we can set up this problem such that it has a very clear solution concept from linear algebra. I'm going to set it up like this. So coefficients, again, there are 2n terms that I need to match. So these two vectors are 2n by 1 in length. On the right-hand side, I need to have eta 1 is 1, and then eta 0 is 1, and then eta 1 all the way to eta to n minus 1. And on the left, it has to be these terms, right? From the first multiplication, I can have a bunch of terms that contributes to the coefficients for the z terms. And from the second multiplication, I can also get a bunch of terms for z inverse, and then all the way to z negative 2n minus 1. Right? So I need to somehow combine them together and see how I can do this. The way that we're going to do is I'm going to do sigma. I'm going to stack this unknown parameter vector with the unknown parameter vector gamma. All right? This is a nicer way. If I can write it this way, I could know immediately when I can expect a unique solution. So how can we combine these? It's actually through a simple matrix augmentation. I'm going to copy down the first set of matrix in here, the one with the alpha parameters. Okay? So this part, multiplying with my top vector, is going to give me the first set of coefficients. And then block, this is essentially block matrix operation, right? I'm going to construct two blocks, M1, M2, multiplying with two vectors, V1, V2. This is going to be M1, V1 plus M2, V2, which is essentially this polynomial equation. All right, so this is my M1, and then my M2 is lying down over there, 0, beta 1, beta n, yes, and then diagonal so that's the structure. So from here, we will know when we can expect the solution for the pole placement. We know that we can for sure do this regardless of this vector here. We will be able to do this for sure if this matrix, for example, is invertible, right? So that's a first approach, right? So let's check the dimensions now. What are the orders over here? We actually calculated the orders already. So the order has 2n rows. This part has n columns. This part has how many columns? N columns, right? So the same thing. So this is really actually a square matrix. So it's 2m by 2m. And it multiplies with a 2n by 1 vector. And it generates a 2n by 1 vector. So good news now, right? So we know that if this matrix is non-singular, we can have a guaranteed solution. And that's actually essentially the good news. It turns out, in fact, if the Planck numerator denominator are coprime, then this matrix is non-singular. All right? We can get some intuitions from here, actually. If beta and alpha, they don't have common terms, let's check a simple example. Let's say this would violate the condition. If I have, for example, Z inverse, let's do this. So in this scenario, denominator is 1 plus D inverse, numerator is 1 plus D inverse, and then a delay operator. So if this is the case, then you can check alpha 1 is 1, beta 1 is 1, beta 2 is 1. The matrix will look like something has 1, 1, 0, 0, 1, 1, and then 0, beta 1, beta 2, and then 0, 1, 1, 2, 3, 4. 4 columns. I need another row. And then this would be 0, 1. So in this example, you can see if somehow there are common factors, then it will appear that some of the columns in the left part of the matrix will be linearly dependent with some columns over here. Okay, you can see how these occur actually. And the good news, however, is that in practice, this is very easy to satisfy. So in practice, we can do pole placement very easily. Okay, quite powerful result, and we're going to use it for this part now. So let's now start to apply this and see the connection. My goal for the next 8 minutes is to help you see the connection with this. Where we have this parameter convergence problem, we know that if this is a series parallel PAA, we analyze the equivalent block diagram that will give us the adaptation error epsilon. We understood hyperstability will give me the convergence for this signal, but we had said it's not necessarily meaning that this is 0. All right? So let's check. Limit this condition simply means, so epsilon k go to 0. From this block diagram, it means as follows. It means the construction is A hat. So this signal minus this signal is epsilon, right? So it's A hat times B over A and UK. This is the bottom branch minus the top branch, which is B hat UK. This will go to 0. And this is equivalently speaking, this is equivalent to, I'm going to avoid writing long equations, I will omit the k index here and just write A hat times B UK minus A B hat UK. This is going to 0. Or I can write it as a polynomial equation operating on U eventually leads to 0. So you can immediately see that this seems to be connected to something like this. A and B, these are constants, all right? So there can be two scenarios. This is basically a larger polynomial. Let's call this alpha 0 plus alpha 1, alpha 2, etc. The order is going to be 2n okay? It's going to be n plus m. All right? So it is a polynomial and it has an order. The question from here is, if you have a polynomial operating on a signal, give me 0. There are two possibilities. One is all the alpha are 0. If this polynomial is 0 itself, then definitely it will give me 0. All right? Another possible scenario is maybe this is not entirely 0, but it can still give us output 0. For example, if we have, so the two scenarios are alpha 1 being 0 leads to equation star to be valid. Then alpha I can also be non-zero, and the same thing can happen, and we don't want that in reality. So we need to understand when this will happen. This can happen, for example, I have 1 minus Q inverse operating on any constant. Yeah, any constant. Okay? If we have this, if U is a constant and then the polynomial somehow give me this, then you can see U0 is U0 multiplying with 1 first. And if you apply a delay to a constant, it won't change anything. Right? You're still going to get 0. So, in a nutshell, it may be possible that this will happen, and we're going to systematically understand when that happened and how we're going to avoid that. And then we're going to understand how we can do this. How we can analyze the convergence here in this scenario such that we can see this will happen if all the parameters are 0. And then we have, so obvious solution is A hat is equal to A, B hat is equal to B, right? So that's the good news. That's the ideal scenario. We have the correct parameter convergence, and all the polynomial coefficients are 0. So we're going to use this part to understand how to do that. All right, that's for today's lecture.